Hello, hi everyone, welcome back to the channel. So today in this video lecture we'll be solving this problem, search a 2D matrix. So you're given M cross an integer matrix with the following two properties, that is each row is sorted in non-decreasing order and the first integer if of each row is greater than the last integer of the previous row. Like in this case, here in this matrix, the first integer of the second row, that is 10, is greater than the last integer of the first row, that is 7. And similarly, the first integer of the third row, that is 23, is greater than the last integer of the second row, that is 20. Now, we are given a target, we have to return true if this target is in matrix or return false otherwise. We must write the solution in log of m into n time complexity. That is, we have to use binary search over this given matrix. So let's see how we can do that. So let's better understand the problem statement using an example. Here we have this search a 2D matrix problem. We have this target, that is 3. We want to search it if it exists in the matrix or not. So one of the ways is simple, just iterate over every element using a nested for loop. That will give me a time complexity of big O of n cross m. Wherever you find the element, just return true. If do not found, then return false. Now, how can I solve this using binary search? Observe the fact that we are given that the starting element of each row is greater than the last element of the previous row. That means these rows are sorted. So if I just open this matrix, if I write these integers like this in a linear fashion, 1, 3, 5, 7, then the second row from here 10, 10, 11, 16, 20. Now start writing the third row, that is 23, 30, 34 and 60. Now this resembles an array, okay, this resembles a linear array, fine. Now this array has a length of n into m, because n into m represents the number of elements that we have in this matrix. Now this element, that is the first element, is low, let's call it low. So we again perform the binary search over this search space, that is over this linear array. So consider this matrix as a linear array and perform the binary search. So initialize the low pointer to the very first integer of the matrix. So low is initialized to 0 and this high will be initialized to n into m minus 1. Why? Because if I write these elements of the matrix into a linear array, then I will have an array of length n into m, where the first index is 0 and the last index is n into m minus 1. So this index is 0, this index is n into m minus 1. Okay. Now the task is simple, just perform the binary search over this linear array. How? Let's see that. Now find the middle element. The middle element is found by the formula, that is low plus high minus low by 2. That would be 0 plus, what is n into m minus 1 here? Here the n into m, there are 3 rows and there are 4 columns. So n into m would be 12 and 12 minus 1 would be 11. So we'll have 11. So the mid would be 11 minus 0 by 2 and that will give me 5. Now we have mid as 5. Now for this linear array the index is 5. Now corresponding to this 5, what will be the element in the matrix? The element here is 0, 1, 2, 3, 4, 5. So mid is this. We are here. But corresponding to this mid, which is 5, what will be the element here in this matrix? It would be mid. We know to reach the mid, we must traverse how many rows? We must traverse mid divided by 4 rows, because in each row we have 4 columns. So to reach an element numbered mid, we have to traverse mid by 4 rows. Okay, so how many rows are there? Mid is 5, mid is 5, so 5 by 4 would be 1. It would be 1. So we have to traverse 1 row. Fine, that means 11, our 11, which is this one, the mid, exists in the first row, in the row number 1, that is here in this row. Now what will be the column for this mid? For this mid 5, the column is, I have traversed, the column would be found by taking modulo the number of columns that we have. So we have 4 columns, so 5 modulo 4 will give me 1. Why? Because we know that in a single row we have 4 columns. So to reach element number 5, I will traverse this 1, 2, 3, 4, 5. So I will traverse 5 elements before I reach our element at the mid, that is 11. So the column number would be 5 modulo 4, that is column number 1. So that means the element corresponding to this mid here in this matrix would be this, and that is present at index number, row number 1 and column number 1. Now in this fashion I will calculate a mid, which I calculated 5, and corresponding to the given mid I will find the corresponding row and the column, and once I found the row number and column number, I will find the element. Like here in this case I found 11 in the matrix. So I don't have to create another array like this. I don't have to create another linear array. I am just visualizing the matrix in the form of this linear array. Now compare this 11 with the target element. The target element is 3. We know that the target will exist from low to mid minus 1, like in this range, because 11 is greater than target. So 3 lies from 1 to 10. Okay, like the 3 lies either in the first row or it lies in the very first place of the second row, that is this one. So let's just reinitialize the range. The range will be reinitialized to low to mid minus 1, and mid minus 1 is 4. So it would be 0 to 4. The new range is 0 to 4. Again calculate the middle element. The middle element will be 0 plus 4 minus 0 by 2. It would give me 2. Okay. Now corresponding to this 2, we are here. Find the corresponding row number and the column number. Row number would be 2 divided by 4. Column number would be 2 modulo 4. So row number would be 0, column number would be 2. That means in the row number 0, the second element, the element at position number 2. So on row number 0, this is the element where we are, on which we are standing. So corresponding to mid equals to 2, we are standing on this element, that is 0, 2. Now compare this 5 with the target. It is greater than the target. That means the range will be again reinitialized to 0 to mid minus 1. The mid is 2, so mid minus 1 would be 1. So this is the new range. Again find the middle element. Now the middle element would be 0 plus 1 minus 0 by 2. That would give me 0. So corresponding to 0, find the row number. So row number would be 0 by 4, it would be 0. The column number would be 0 modulo 4, it would be 0. So that means check the element at 0 0. The element at 0 0 is this 1. Now compare this 1 with the target element. We see the target is greater than 1. So reinitialize the range from this, that is mid. So mid is 0, from mid to high. So the range is 1 1 now. Again find the middle element. Now the middle element would be 1 plus 0 by 2. It would be 1. Now find the row number corresponding to mid as 1 and the column number. The row number would be 1 by 4, that is 0, and the column number would be 1 modulo 4, that is 1. So for row number 0, get to the element which is here, that is this one. So 0 1. So find this element. Now corresponding to this element here, compare this with the target. I find that this is indeed the target, so I return true here. So in this fashion the binary search will work here. Let's just jump to the code implementation. So this is my function, this is my search matrix function. Let's find the number of rows. We have matrix dot size number of rows. Find the number of columns, that would be matrix 0 dot size. Now initialize the range. Low will be initialized to 0, high will be initialized to n into m minus 1. Run the usual binary search, low less than high. Now find the mid element. It would be low plus high minus low by 2. Check if the middle element. Now find the corresponding row for the mid. It would be mid by m, and the corresponding column would be mid modulo m. If the element here is basically greater than target, if it is greater than target, then reinitialize the range to, like if it is less than target, let's take this condition. If it is less than target, then that means the range will be reinitialized to mid plus 1 to high. Otherwise the range will be reinitialized to low to mid minus 1. So high will be reinitialized to mid minus 1. At the end, after you run this binary search, check if the element that you have found, so low divided by mid, low modulo mid, because here in this low will have the element, will have the position of the element if it is present. Okay, so here in this low will store the lower bound, will store the lower bound will be stored in low. Okay, so this is a strategy to find the lower bound. Now check if the element at this low, if the lower bound is equal to target. Remember the definition of lower bound. Lower bound is an element in a given sorted array which is at least equal to the target which we are searching for. So check if the lower bound is equals to the target. In that case the target is present. If it is not, then the target is not present. So let's just, okay, it worked. So in this fashion I will search for the target in a given search matrix. So let's just calculate the time complexity. We can see that the search space for this given problem is this one, that is n into m. We are searching into n into m elements. Now if the search space is n into m and we are using binary search, the time complexity would be log of n into m to the base 2, and that's what we required, and that's the answer, while the space complexity is constant because we are not using any extra space. Fine. So that's all for this video. If you like